So welcome to our Introduction to Networks course meeting for this week. We're again, I asked you last week to go ahead and go through and watch the chapters on, or watch some lectures on IP addressing and standard subnetting. One of the things I want to do is I want to make you aware that I know we're getting toward the end of the course, so I want you to be aware that I know we've got still a good amount to do in course. We have some time after the course, quote, officially ends. I will not be closing this course in NetAcad. In fact, this course will be open probably all the way into May as we move forward. So no one's allowed to freak out. That's my rule. There's no freaking out. But we will have, obviously I've skipped some chapters here. I've jumped past the physical layer stuff, skipped a little bit of the data link stuff, because a lot of that's Network Plus stuff that you can read and understand without much issue. Now, having said that, it is very important that you read chapters 4, 5, and 6, and that you understand the process of ARP, and you understand MAC addresses, and you understand how Ethernet creates frames, and CSMA-CD and CSMA-CA. Those concepts are important. I just want to move forward, though, because honestly, those are very important, but IP addressing is immensely, immensely important. So, I'm not going to go into really kind of this chapter 6, which is looking at a router, what a router is, and those types of things, and even this basic configuration of a router. Well, yeah, I will. I'll do a little bit of this. So, actually, we'll come back to that. I want to stay in the theoretical until we can do some of this. But we're going to look at addressing of IP with IP addresses. And one of the things I always tell people is computers are some of the most unintelligent devices you've ever seen, because literally they know ones and zeros, and that's it. They are binary. Everything to a computer is a 1 or a 0. It's either on or off. Well, for the computers we're using until we get to quantum computers, in which then it's 1s, 0s, and something else. Who knows? But for our modern computers, especially with IPv4 addresses, we've got these addresses that are 32-bit dotted decimal. So, one of my favorite things to always use is just a little notepad here. I was going to get my Surface tablet up and running for this class, but I got caught up in some other stuff, and so I won't be able to write. But if you had the IP address 192.168.10, I'm gonna be lazy. I'm gonna be very lazy, folks. 192.12.10.1. That's an IP address. Okay, that's dotted decimal format. That is 4 octets. So an octet has 8 bits in it. So each one of these units, each one of these octets, is an 8-bit section, and each one of those bits is a 1 or a 0. And they are represented by powers of 2, since it's a binary numbering system. So you've got from 2 to the 0 up to 2 to the 7th power, which we'll see a little bit later. But the computer doesn't see 192.168 or 192.12.10.1. It sees 1, 1, 2, 3, 4, 5, 6, 7, 8. I think I just made too many. 1, 2, 3, 4, 5, 6, 7, 8. Yep, 1 too many. And then 12, 1, 28, 64, 32, 16. 8, 4, 2, 1, and then 10, 1, 28, 64, 32, 16, 8, 4, 2, 1, and then I think I did that right. So got 1 too many on. 1, 2. Yep, that's right. So that's what the computer sees. It sees these octets, and I'm going to take the dot out for just a second and just put some room in here so we can kind of see these pieces a little bit easier. But each of these octets is 8 bits, and each one of these is represented by 2 to some power. So in this case, obviously this is the first bit position, so this is 2 to the 0 power, and I have to carry it out, which is very hard to do with this. Again, the reason why I needed my Surface tablet. But 2 to the 0 power, which is turned on, which is 1, and that gives you the value 1. Now, computers, because they are binary, it's important that we at least understand the basics of conversion. So here we have dotted decimal. This is what we see because we don't speak binary very well. This is what the computer sees. and it's what the computer works with when it's trying to do things. Like I mentioned in other courses or other parts of our class, I mentioned the concept of how you, and if you watch my video, how you AND to an IP address together with its subnet mask to get a correlating subnet or network that falls through. That's how a computer works with this information. And here's an example again, same thing I just showed you. Here's our octets, 8 bits, and it is a 32-bit address because when you look at it, there are 32 bits. Be aware too that 4 bits is actually a nibble. That's not a joke. That is an actual term. It's not really used much, but it is just fun when you're trying to impress your friends at a dinner party. You say, hey, did you know 4 bits is a nibble? And there's a good little video here that you can walk through looking at how to convert between binary and decimal numbering systems. Looking at, this is really good, especially if you're teaching this class to students who are, I won't say mathematically challenged, but maybe not strongest in math. It's good to go over how we use a base 10 numbering system and how they've been using this their entire life. And it's no different. It's just that we're now, instead of using a base 10 numbering system and raising it to the power 10 to the power of its individual position, the radix, we're using base 2 numbering system. So we're using a binary numbering system. So 2 to the 0 power is 1. 2 to the 1 is 2, 4, 8, 16, 32, 64, 128. And of course, if you go on, 5, 12, 10, 24, et cetera, et cetera. But this, I think, when you show them the base 10 and then base 2, it helps them understand a great deal more what the difference is between, or really the similarities, not even the differences, the similarities between the base 10 and the binary positional notation. Now, conversions, you can watch the video, but you basically can do subtraction, or you can do, if you're doing converting from binary to decimal, you do the addition method. So you take and add the values up. So here we see it. If the 2 to the 7th position is turned on and 2 to the 6th is on and nothing else is on, we would add 128 to 64, and that would give us 192. You also will learn as you go along some of the different things of how 1 and all zeros is 128, 1, 1 is 192, 1, 1, 1, 224, 1, 1, 1, 1, 240, 248, 252, 254, and 255 if every one of them are turned on. So you learn those things, and you learn how to convert. It's still easy to make mistakes if you're not careful, but you also will learn, here's something that I always teach students. If the 2 to the 0 position is turned on, the number will always be an odd number. If it's turned off, it will always be an even number. If it's turned on, it will be an odd number. So you see here in the 11, the first position is turned on to the 0 position. And that kind of helps them keep themselves in check to know if they made just a really dumb mistake, an easy mistake they can fix. And this goes on through, and if you're going from decimal to binary, you can do the subtraction method. So you take a number. Can you subtract 128 from it? If the answer is yes, you turn that position on, subtract 128, and continue on. So it's actually just go all the way through, turn on the items that you can subtract, and then when there's nothing left over, everything else is a 0. So here's an example. You've got 192. So greater than 128, yes, turn on that. Subtract 128 from that, which leaves you with 64. And then now you can subtract, is it greater than or equal to 64? Yes, it is. So we're going to turn that on, subtract, and then you've got your number. So you can go through and do your conversions. And here's obviously a good example. 168 greater than or equal to 128, yes, leaves you with 40. I then cannot subtract 64, so we put a 0 there. But then I can subtract 32, which leaves me with 8. Can't subtract 16, I can, so on and so forth. So that's binary to decimal conversion. Oh, that was actually decimal to binary conversion. And before that was binary to decimal. Okay. Now this is a concept that I really stress to my students, and that is that all IP addresses, there's a couple rules. Okay. There's a couple rules that we go by, and that is that all IP addresses are made up of a network and a host portion. Okay, so that is a given, a network and a host portion. Now, as part of the network portion, you may have a subnetwork portion, but there will always be at least a network portion, a possible subnet, and a lot of people, really, when you look at a lot of the documentation, you will see many books just call it the network portion because, I mean, technically the subnetwork portion is part of the network, but there's a host portion. Now, here's something that's very important. The host portion can never be all ones or all zeros. Okay, and let me reverse that because we would probably say all zeros first or all ones. Anybody know why?
One's network ID, the other one's broadcast.
Bingo. The zeros, if it's all zeros in the host portion, exactly, then that's the network. If it's all ones in the host portion, that's the broadcast. All right. Sorry, folks. I'll be back 1 second. Sorry, folks, boss on the other line. All right, so that is true. They cannot be all zeros or ones. Very important concept. And that's also, by the way, how do you figure out the host portion of an IP address versus the subnetwork portion? Do you remember? Oh, dang, I think sorry, John, I accidentally muted you. Do you remember? ANDing. Yep, that's exactly right, Scotty. You go in and you AND the IP address to the subnet mask. If you don't have a subnet mask, all you can do is assume that the IP address is using classful addressing. And that's what my other lecture was on, was the idea of classful addressing. In this case, a 192, that is a class C, so we assume that it's classful. So the first 3 octets are the network portion, and then the 4th octet is the host portion of the IP address. And that is, we can only assume that. It may not be true. It may be, you know, this could be instead of this is what would be called a /24 because there are 24 bits in the subnet mask. But if it was a little different, it could be a /27, and that would change completely what we're looking at here. So here we are, subnet mask. The purpose of subnet mask is to define what portion of an IP address is the network and subnetwork portion, and what portion is the host portion of the address. And again, the easiest way to find out if you don't know what portion is what is to AND the IP address to the mask, and then the network will fall through. That's what's left when it falls through. Okay, so there's your subnet mask. And again, here's your ANDing. And when you do that, that gives you the portions that are your network versus host. Here's our logical ANDing where we go in, a 1 and a 1 is a 1, a 1 is 0, 0, 0 and 0, 0, 1 and 0, 0. Now, okay, all the math people out there, please close your ears. I teach my students to just multiply them together. I know it's not multiplication. Please don't jump all over me and get mad. But you know what? It works the same way in the end. So for many of our students, that's the easiest way for them to understand is that when you logically AND something, the end result is the exact same thing that would happen if you multiplied them together. So how do we do this then? We go in and we say, hey, I got this IP address in binary. I got this mask in binary, and then I AND them together, and what falls through is 192.168.10, which happens to be, now notice, here's a very important thing related about what we talked about earlier. Notice now, once I do my ANDing, notice all the host bits are zeros. So that tells me that this is my network address, okay? Same thing would happen if we were doing a subnetwork. You would have all zeros in the host portion. Some good activities in here and to actually go through and do some ANDing. And you can actually, here's the great thing about this, you notice you just keep clicking, it keeps giving you more examples. So your students can try as many as they want until they get to where they can actually do the ANDing. Now, one of the things that we talk about prefix links, we have some prefix links that we use /8, which I mean they're 8 network bits, 16 all the way down through /30. And you cannot have more than a /30 in terms of for a true network. You will see a /32 on occasion when you're trying to advertise a single IP address, or your the nomenclature is for a single IP address. That means all 32 bits. But typically a /30 is the smallest we can get in a subnet mask, because you've got to leave at least 2 bits for the host. And that is because there's a formula, 2 to the h minus 2, which is the number of hosts in a subnet or in a network. And if there's 2 bits, 2 to the second power is 4 minus 2, which leaves you with 2 host bits, usable host bits. And that would be because the first bit is always for your network ID, and the last bit is always for your subnetwork ID. So here again, we got a network address, and we got to find out what the host address is, and then the first usable IP address in that network address, and that would be the first address that is not all zeros in the host portion. And then the last host address would be the IP address that's not all ones in the host portion. And then the broadcast would be exactly the opposite. So here we have 192.168.10/24, that's our subnet. First usable host is 1. Last usable host is 254, and then 255 is the broadcast for this particular network. All right, does that make sense? This stuff you already know completely. I'll move on pretty quickly.
No, it's a refresher.
Yeah, it is good to refresh, and I think it's really, again, important that you do use in this /24 kind of a class C. To give students the ability to see just from the beginning a classful address. Then you can go from there. And then we got all kind of. So statically assigning versus dynamic assigning IP addresses to a host. We've gone over this already. Looking at DHCP versus static IP addresses. Unicast 1-to-1, broadcast 1-to-all, multicast 1-to-some. I do like these videos because it does show you, for that visual learner, how, especially multicast. I think multicast is important because you see these 224 numbers and you see that it goes out to some, and these other ones still receive it because it's still technically being sent. Okay, unless you're using some type of multicast filtering. Otherwise, it's still being sent to all ports, but only the machines that are configured with a multicast address will listen. So. Again, unicast 1-to-1. I'm not going to spend that much time there. 1-to-all. By the way, what do you think? What the IP address is for a broadcast, or where do you think that?
Again?
What is the IP address for a layer 3 broadcast with IP?
Layer 3 broadcast?
Yep. So a network layer IPv4 broadcast. Where is it sent to?
Oh, just on the network.
Okay, what address?
Oh, it's all 5. I mean, all 255s.
Correct. All 255, 255, 255, 255, which make sure your students know what happens when you convert this to binary. It's all
ones.
It's all ones, exactly. So this is the broadcast address for an IPv4 network. 255, 255, 255, 255, because it's all ones. Important for them to know that. And just good, good general dinner party information. Now, what about private versus public IPs? Now, I'm going to tell you right now, it's not for the RFC 1918 addresses. And that's one of those, I've kind of started telling you all my secrets about I always give my students the thing, what if you were at a dinner party and somebody walked up to you and said, hey, what do you know about RFC 1918? And I tell my students, or they called you and said, I give you $1 million if you can tell me about RFC 1918. I want them to be prepared to say, oh, that's the private IP addresses, IPv4 addresses. But without these, we would already have all been running IPv6 in our houses. IPv4 blocks have been gone for a long time, and now we are using these private address blocks and using NAT to convert to public IP addresses. But this block, which you really need to know, is 10.0.0.0/8. So entire Class A 10 network. 172.16.0.0 /12 to 31, or /12, so 16.0.0 to 72.31. 192.168.0.0/16, which is the collection of 255 Class C networks that exist underneath that. And these, the weird thing about these is these IP addresses can be routed internally, but at any ISP, those ISPs have configured their network so that you cannot actually bring traffic in or have traffic routed in any way with these addresses onto the network. Now, there may be some funkiness somewhere in the world where somebody, an ISP, is actually running private addresses inside and then doing some on the very outside edge of their network connected to the true internet is running public IP addresses. But these addresses cannot be routed across the internet. So, but they're still widely used. For instance, a great number of networks today use the 10. The 10 network, they use it, they subnet it for their internal network, and then they go from there. Other addresses that are important, if you've ever seen the t-shirt, there's a couple t-shirts that says there's nowhere like 127.0.0.1, which is home. It's ping 127.0.0.1, you're pinging the loopback address, which is a reserved address that is running on the IP stack of any device running IP, which lets you prove that the TCP/IP protocol stack is at least running on a device. Now, that doesn't mean that the IP address on the machine is correct or that anything of that nature. It just means that the TCP/IP stack is running. You could have a misconfigured static IP address. You could be handing out the wrong DHCP addresses. This only proves that you are indeed at least running TCP/IP. We also have link local addresses. I call them a PIPA, automatic private IP addressing. They were used and are used by Windows clients when they boot up and cannot find a DHCP server. They will give themselves a 169.254 address. They'll actually pick an address, ping the segment, see if anybody's on it. If not, then take that address. When this first came out, when Windows 95 came out, booted a machine up and it didn't get to a DHCP server, and it suddenly got a 169 number. Well, I'd missed the memo that they were using this, and in fact, everybody that was working with me had missed the memo. And we were like, all right, somebody's got a rogue DHCP server, and we were looking for it everywhere. And then we figured out, hey, wait a minute, okay, I know what this is now. We also have testnet addresses, 192.0.2.0/24, and those are set aside for teaching and can be used for documentation. So if you see them on the internet, you'll see that sometime. And then, of course, experimental addresses, which are 240 to 255 up through there. That's the Class E's. So here we have legacy addressing, and this is one of the things that's very important for your students to understand, is that there used to be Class A, B, C, D, and E. Okay, well, there still is. I mean, it's still there, but we just don't put IP addresses out in those in just those 5 formats at this time. Class A was anything from 0 to 127, and that is anything that starts with a leading high order bit of 0. And it allows for 128 networks. Now, one of the reasons why people go, well, it's the entire first octet, why is it not 255 maximum networks? Well, the first bit has to be a 0, so there's one reserved. So that confused me for the longest time. and that's why it's 128 versus 256 possible 0 to 255 or 256 addresses, because that one bit is reserved. Class B is 128 to 191, and the first two bits must be 10. So when you take those out and then look at your leftover bits, that's why you only have 16,384 instead of 65,536 for networks. And last but not least is our low lead Class C, which is 192 to 223, and it is 2 million networks of 254 hosts, and the first three bits must be 110. Now, Class D is 1110, which is 224 to 239, and then anything from 240 and over is Class E. So you will see that on occasion. You'll see Class D for your multicast block and everything above. And again, it's just based upon the bit, however the bits are turned on in what order. Now, the problem with classical addressing is it was not very useful in terms of being able to actually hand out IP addresses in a good way. You could hand out a Class A to somebody, and if they didn't subnet it, and even if they did subnet it using classical subnetting, you could still end up with a huge amount of wasted addresses. And again, you should have seen that in my other two videos on subnetting, Chapter 6 that I gave you. So what we did is I said, we got to do something different. We're going to assign IP addresses in a classless way. In other words, we're going to go in and just give you a prefix. Now, the other thing they did is, hey, we need another type of IP addressing because we're going to run out of IP addresses. You'll notice here, IPv4 exhausted in July of 2015. 2012 in Europe, that's a long time ago. Africa is expected to exhaust in 2019. They've all been allocated to AFRINIC. They just haven't actually been sent out to ISPs for use. And look at this. In Asia, they exhausted in 2011. So there was a huge need, and there's still a huge need for IP addresses. I had to redo my network at home this past weekend, and suddenly realized the number of devices that I have on my network with IP addresses. So you think about your common home. You've got, a couple PCs, a couple laptops, a couple phones, tablets, game consoles, direct TV boxes, Comcast boxes, et cetera, et cetera. Suddenly you've got 15 to 20 devices per home. And so IPv4 addresses are pretty much gone. We also have now the Internet of Things, or Internet of Everything, IoT, where we're going to have so many different devices connected to the network. Now, you can coexist IP and v4 and v6. Now, one is an item they call dual stack, and this is we're going to literally run both on a machine. Now, a lot of people don't realize it, but IPv6 is turned on by default in Windows 10. So many of us are running Windows or IPv6 and don't even know it. I would suggest if you are not, and people always laugh at me because I'm still running Windows 7. Because, quite honestly, I haven't had time to upgrade my desktop. Every other machine I own, except for the one in front of me at my office, is Windows 10. And this one, I just cannot seem to find time to actually upgrade. But even still, in Windows 7, IPv6 is turned on. So one thing you could do at home, if you're paranoid, which is probably not a bad thing, you could go in and turn off IPv6 by simply unchecking the IPv6 protocol. This will actually provide some protection for you, because there are some attacks using IPv6 tunneling or IPv6 and IPv4 tunneling to try to do some nefarious things. So if you don't want IPv6 on, you can just uncheck it, and that will turn it off on your particular interface. I'm going to cancel that just for the fun of it, because I'll end up trying to do an IPv6 lab and it won't work for some reason. So one option to run both is dual stack, run both protocols. Another option is to tunnel in this manner. So we take an IPv6 network, we run a dual stack router on one end and a dual stack router on the other, and you tunnel IPv6 and IPv4. So that is possible. And then you can do translation. You can do a NAT 6 to 4 or 4 to 6 and translate between the two. The end goal, though, is to get to where you're running really running all IPv6. We are a long ways from that in the United States of America. In other parts of the world, we're in better shape because of some of the facts that, A, they run out of their IP addresses in 2011, so there are some Asian countries that have been pushing IPv6 much harder than the U.S. We're still a good ways away in the U.S. Okay. Notice that IPv6 addresses are hexdets. Okay, so there are 4 hexadecimal digits, or 16 binary digits per hexadet. There are 128 bits total in IPv6, which, just to give you an idea of how many IP addresses that is, I have been told and have read multiple places that there are enough IPv6 addresses in this setup to give an IP address to every grain of sand on the planet. That sounds like it's crazy, but at the same time, it is that big of an address space. Scotty has a very good question. That is, how will security work since there will be no more NAT and PAT, or there will be some other way to separate a LAN? Well, one of the things I want to kind of throw out here to you is IPv6 addresses are 128-bit addresses. Okay, so you've got /128 is the entire addressing scheme. Typically, there's a /64 network portion. Okay, and then there is a obviously 64 host portion. Well, inside of that /64 network portion, or network prefix, they call it network prefix, there's a standard that says you'll take /48 bits to be your network prefix. Okay, and then you will have another /16 bits to be your subnet prefix. Okay, and then you will have your /64 for host. Now, the current working model is that we will have /48 prefixes handed out to everyone at their homes. Okay, so think about this. That means at your house, you're going to have 16 bits. You have 2 to the 16th. And I might do the math on that, because what is it? 2 raised it to the power of the 16th. And you're going to have I should know that, 65536, sorry. Long day. But at home, you'll have 2 to the 16th, so 2 raised to the 16th power subnets for just your house. So you have 65,536 subnets for your home. Now, each one of those subnets will consist of 2 to the 64 hosts. All right? So if we take 2 and raise it to the 64th host, you've got that many hosts in 65,536 subnets. So, in theory, imagine that you randomly pull a subnet or assign a subnet and then randomly pull an IP address, a host address. Now this is not using EUI and all this type of stuff either, but you use a random host. If you do that, you basically are at the point where people would have to scan for centuries to find the IPs on your host. So basic knocking on the door port scanning is going to be much more difficult. Impossible? No, but much more difficult. The other thing is IPv6 does have some built-in abilities. They built in some security features to where you can actually use some IPsec features. The problem is it hasn't been totally implemented either. So quite honestly, we don't have an absolute wonderful answer for how is security going to work. Now let me say this again. NAT and PAT were never meant to be security features. A lot of people consider them security features because they are hiding the internal network. The problem with that is many people would say that they are actually a detriment to security because guess what? That botnet on the campus network hides behind the NAT that is running on the campus network. If you were running an actual IPv6 and had a true public address on your machine, I could trace that botnet back to the individual machine that is producing the botnet activity. So the answer is we don't fully know yet. But that's the best answer I can find, is at least port scanning is not going to be as easy as it used to be, because the address ranges are so big that it'd be unreal. Scotty says, this isn't part of the IPv6 based on MAC address, so the subnets will separate it, correct? It depends on the operating system. If you use EUI, and I believe, let me go forward here. I'm pretty sure it's going to show these rules here where we omit these rules you need to know for naming of how you can actually show IPv6 addresses. You can omit leading zeros. That's one rule. Okay. The other rule is you can omit all 0 segments, so you can actually just leave them out and put a colon. So if this is all zeros in here, you put a colon. You can't have 2 colons, or otherwise you wouldn't know where the segments were actually, how long each individual section was. But here we have obviously source destination IP addresses, just the same. Prefix link, here's your interface ID. Now, if we're using what's called EUI64, the MAC address is used to create that IP address. But Windows operating systems quickly stopped using that because they realized that there were some major issues with that. So now Windows operating systems will actually randomly generate the DHCP host portion, and so it's all randomly generated now. And that was because they figured out EUI was a bad thing. You know, if you've got someone trying to track somebody, then obviously EUI is bad. And so that's one of the things they did away with pretty quickly. Most operating systems today do not use EUI. Here is that global routing prefix again. Your global routing at 48, 16-bit subnet, 64-bit for your interface. Got that there. So the beauty is subnetting is a whole lot easier with IPv6 because your subnets are subnet 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, actually, it's 9, A, B, C, D, E, F, and then so on and so forth. Setting an IP address on an interface, IPv6 is very easy. IPv6 address. You do want to turn on IPv6 unicast routing if you want it to actually be able to route those addresses. So you can go in and statically assign the address. For PCs, you can statically assign the address, or you can have them. There's multiple ways of getting an IP address on a host. One is static. One is doing it automatically through what is called stateless auto configuration. Or you can do stateful DHCP v6. We'll talk a little bit about that. Probably have to do that in our next course, next class. So actually stop here because, like I said, if it's 4:57, I might have to jump into the other course. Are there any questions? I'm going to stop this. We'll pick up here and move on as we continue going.